Any issues with that, then escape now while you can. So thanks for joining from wherever you are in the world. We've got a couple of exciting presentations. The first one from Kobus and the second one from Edward, focusing on leak initiation and evolution of those leaks in pipes, particularly with reference to pressure. The first presentation we got from Professor Kobus Van Zyle. He's a professor at the University of Auckland, previously from the University of Cape Town. He's done a lot of work in this area. So Kobus, I don't know if you can share your screen and just get started there. Thank you.
All right. Is that working?
Yeah, I can see that. I can hear you. Excellent. I'll go on mute now. Oh, I should say, actually, we're going to take questions right after each presentation. So if you do have any questions, please just drop them in the chat and then we'll address them at the end. Thanks.
I can go, Joseph. Looks like it. You've muted yourself, so I'll go.
Oh, go for it. Yeah, please do.
Thank you. Thanks for the opportunity. It's lovely to be presenting at the series. My interest in leakage started in 2021, just after I finished my PhD at the University of Exeter, when I attended a workshop by Alan Lambert, who's with us today, and John May at the Montfort University, where they talked about pressure and leakage, and that really piqued my interest. And I've been working in distribution systems as my research, but a particular focus has been the behavior of leaks. So before I start the presentation, just to acknowledge that many people have contributed to this. Two practitioners I'd like to highlight. The one is Alan Lambert, who's been greatly supportive, and Mark Shepherd, who have both shared a great deal of knowledge and data and wisdom. We've had several water authorities and funders who supported the work, and then of course many postgrad students who's worked on it. I've tried to put their names on the slides below the heading where there's a particular contribution, just to acknowledge them, but there are many more that I'm not listing. So I want to start this presentation with what I call a conundrum, and this is the link between pressure and burst rate. The data you see at the moment is for asbestos cement and polyethylene, data that we analyzed for the city of Auckland, and you can see there's a very nice correlation, linear relationship between pressure and the burst rate. For both of them, the slopes are remarkably similar. I did cheat a little bit, and that I didn't. Let me just get the laser pointer. There's one point there on the polyethylene that I didn't include in this relationship. It seems like the plastics may be like more of an exponential rise towards the higher pressures. But anyway, this is just to show there's this relationship between pressure and burst rate from the data. And this is steady state data. So in other words, this is the same system, pipes, the same pipe material at different pressures in the system, and we're comparing their burst rates. Now, the behavior when you do pressure management is somewhat different. And this is Alan's model for pressure management. And this is the model described there. It says that you've got pressure independent bursts that you have to subtract. And then there's pressure dependent burst, and those burst as a function of the pressure to the power 3. So cubic function of pressure, very strong function of pressure. And so if we take for instance, the AC relationship for Auckland there, and we say, let's start with a pressure of 110 meters there, or 100 meters, and we have a burst rate of 40 kilometers per 40 failures per 100 kilometers per year. And then we reduce that pressure to 50 meters. And if it's a steady state, the burst rate would drop to 30 failures per 100 kilometers per year. But if it's a pressure managed zone, according to the model, the burst rate will drop to about 20 failures per 100 kilometers a year. And the question that we started this exploration of is, why does that difference? What causes this not to be the same? I'm going to try and give a part answer through the work that we've done. So first, I'm going to talk about how failures happen. So failure happens in any structure, like a pipe, when the load exceeds the strength. The load on a pipe can be external, and there are various external loads, but there's also, of course, the internal load, which is mainly pressure, and it's the combination of the two that will give the maximum load at any point. The strength of a pipe is, firstly, it's not the same everywhere. So the pipe's not going to fail over the average length. It's going to fail at the weakest point. So that should what we're interested in. And the second thing is that the pipe deteriorates over time. And so the strength will reduce over time. So the loads vary, but also the strength deteriorates over time. So we're trying to understand those processes. So just look at the internal pipe loads, and that's pressure. This diagram just shows over the life of a pipe that you've got variations. There's a field testing initially that's quite high pressure, and then you've got seasonal variations, you've got diurnal variations, you've got background pressure fluctuations, transient noise, and then you've got big transients as well. And you've got periods where you empty the pipe, you reduce the pressure to zero, maybe for repairs or whatever. And so these are the loads that a pipe is subjected to internally, and it varies. If we look at the pipe strength, this diagram just represents, if you take all the points on the outside of a pipe, you expect a normal distribution for the strength on the outside of the pipe, but this indicates that there may be a couple of points on this pipe that are weaker than general, and that may be because there's a manufacturing defect or it's been damaged when doing construction. And this is important because this is where the pipe's going to fail when you pressurize it. So we have weak points on the pipe, and then we have the deterioration mechanisms that disproportionately work on these weak points because they already have, more surface area. Maybe there's stress intensification happening. So we've got the weak point and then deteriorating at some point over time. The weak point will start to leak. It'll breach the wall, and then we have we call a background leak. It's leaking, but it's too small to be detected. That background leak will continue to deteriorate and grow until we get to about 250 liters an hour. And then I'm calling it a potentially discoverable leak. So the leak is now big enough that you can discover it if you go and look for it, but you don't necessarily look for it at the time. And so it's going to continue to grow until it becomes discoverable. It's discovered. So it becomes obvious that there's a leak from pressure or water appearing above the surface. So there are two aspects that I want to talk about. The one is the deterioration mechanisms. I want to just explain and show what they are. And the other one is the leakage flow rate, because the flow rate is one of the main mechanisms that makes a leak discoverable. And so if we look at, and I'm particularly going to be interested in how does pressure affect the deterioration and failure flow rate of pipes. So the first deterioration mechanism is corrosion. There are different types. And I'm throwing out the equations here, but it's really just to point out certain things. And what I want to show here is that the deterioration is a function of time, really, in that equation. Pressure doesn't play a role, although you might think it. You can have a bit of an influence. The second mechanism is what I call soil erosion. And this is something we discovered in our experimental work at University of Cape Town. And where you have a leak, now I lost my, oh, there we go. I think that'll work. No, it doesn't work. Sorry, I'm trying to play the video, but I'm not sure if I will be able to. No, because I changed the cursor and I don't know how to. Erasers.
Turn off your laser pointer, Kobus.
How do I do that?
Great question.
Let's see if
Let me. Oh, yeah. You maybe click on laser pointer. Pointer option.
pointer options and no.
No, that's not it.
No, and yeah. So let me just explain what's happening here. This is a leak we created in a glass bowl with a glass side, and you're seeing what we use there is a glass beads, uniform glass beads as a soil medium. And what you have is this fluidization of local fluidization happening in the soil. And this is an interesting problem in itself. How does this happen? How does it operate? But the interesting thing for pipe deterioration is that you get the scouring of the pipe, the soil particles. They're picked up at the bottom here, transported to the top there, and then they move around and they scour across the surface of the pipe. And that's very much a function of the flow rate. And so pressure plays a role in that rate of deterioration. And so that is the second mechanism I wanted to show. Okay. Now I'm completely stuck. Right, so I think what I'm going to do is just...
I think maybe if you stop sharing, Kobus, and then just reshare, that might be the best way to do it.
Do that. Yeah, let's do that.
All else fails, just restart.
I won't start from the beginning, I
No,
promise.
no.
Okay, let's see. I can't. Oh, there we go. I managed to close the presentation. Apologies. So let me share the screen again. There you go. Okay, is that visible now?
Not yet. Let me.
Oh, wait, share. Oh, sorry, there we go. Share and now?
Yes, yep, you're there.
Okay.
Great stuff.
Well, okay, now I'll play the video. So there you see the movement of the sand particles, the local fluidization, and the scouring of the surface of the pipe there. And this, I mean, you see this on pipes from the field. This is a collar that had a leak at the seal there, and you can see the hole that it's scoured there. And so this is affected by pressure because pressure affects the flow rate, and that drives this mechanism. The third deterioration mechanism is fatigue cracking, and this is a PVC pipe from the Netherlands that it has a longitudinal crack, and you're seeing the inside of the crack walls. There's a weak inclusion there that created this, and what you can see there is these lines, and they lines indicate points where the crack length was. So the crack didn't happen all at once; it sort of grew slowly over time until it reached, until it was long enough to really break. And then this is a function, this is interesting because the length of the crack, which is A, is not a function of pressure, but it is a function of the change in pressure. So the pressure variations and the number of cycles that drives this process. And then finally, this is a fracture at some point based on the length of the crack and the pressure, you get a complete catastrophic failure that you see there. We used a hydraulic balloon to pressurize it. but just to illustrate that process. So those are the mechanisms. Then when we look at the area of a crack or a leak, we also know that that area varies with pressure. And we know that it varies linearly with pressure. And this diagram shows, I'll come back to the picture in a moment, but this diagram shows the area of a round hole with pressure. And you can see round holes are completely stable. They don't change, so they act like orifices. And the same behavior occurs with small diameter steel pipe or metal pipes. These are longitudinal cracks, and they vary greatly with pressure. The crack open up if you increase the pressure, and so the area increases. The green there is circumferential cracks. They slightly decrease in area, but depending on different conditions, they can also increase. And what you see is that they're all linear functions of pressure. This equipment there was to look at what happens under negative pressure. So we increase the pressure on the outside of the pipe. And so what you see on these curves is when we go to the negative pressure, the area line actually continues. So a longitudinal crack will open with increasing pressure, but if you have a negative pressure, it'll decrease the area of that crack. And we understand this process quite well. We can predict for a given pipe what the slope will be of a line. So that brings us to the Favart equation, which all of you will have heard about or know. John May famously introduced that. This is the orifice equation, which describes the leak, the flow rate through an orifice is a function of the square root of the pressure, and of course times the area. But if the area is not fixed, but is a linear function, so it's an initial area plus the slope, we call it the head area slope times the pressure, then we get to this, which is called the Favart equation. And this has two terms, h, the pressure to the power 0.5, and a pressure to the power 1.5. And so this is what John May pointed out, and it explains why the N1 leakage exponent can be between 0.5 and 1.5. This applies to individual leaks, and with our understanding of material science, we can actually predict for a given leak what M will be. But it also applies to a network or a DMA with many leaks. And so if you apply to DMA instead of the N1, you can get the total initial area of all the leaks and the total slope, head area slope of all the leaks, which I think we should be using more because it's a physical value linked to it. It's and they're constant. But anyway, so this is the Favart equation of flow rate. And it's important because the flow rate determines when you can find a leak. So if you have a longitudinal crack that opens up with pressure, you're going to find that crack at a lower pressure than you would a round hole with the same area. So now I want to move on to a model that I developed with one of my students, Lunita Vega, on how do we model this process of age and pressure. And this is a graph. I'll explain what it means. It's a little bit confusing, but this is failure rate per kilometer per year. This is age of pipes, and each of these lines represent a different pressure range. And this is for PVC and from our data of Auckland. So what the data shows is that the lower pressure pipes have the lower, the lowest value slope there. And as you increase the pressure, you get that the slope actually increases. That's the sort of general trend, that the failure rate increases, but also the slope seems to increase a little bit. And so we then said, okay, we can model this process. And so that's what we did, was to say, okay, let's plot age, pipe age, against a pressure on this axis. And so 32 there is because the average PVC pipe in Auckland was 32 years old. And so we said from the data, if the pressure is 70 meters, we know there'll be 5 failures. So that those dots represent 1, 2, 3, 4, 5 failures in that year for a typical DMA. But if the pressure is 55 meters, there'll only be 4 failures in that same year. And we also know that this failure rate will increase with time. So we can model this over more years. And although it looks like these dots are equally distant, actually they increase. So there are four dots in that year. But if you move there will be there's 1, 2, 3, 4, 5 dots in that year. So the failure rate increases. And then we said, what we think is happening is that, a failure that'll happen at 70 meters will only happen later at 55 meters because it needs more time to deteriorate more. It has to grow to a bigger size, a longer crack, a bigger hole before it's going to reach the flow rate required to be detectable at 55 meters. And so we drew these lines. Now, each of these lines represent an individual leak in a DMA. So, and when the line crosses the pressure in the system, that leak becomes discoverable. So what this shows is that, this leak was discoverable at, year 32 at 70 meters. But if the pressure is 55 meters, it needs to grow the crack or develop the hole. And so it's going to take more time, and only maybe 2 or 3 years later, we will discover it at 55 meters. So this was our conceptual model for leakage. And then what we could do was to say, let's now model a pressure management implementation. So we said, okay, let's keep the pressure at 70 meters and then drop it to 55 meters. And then we see what's going to happen with our burst rate. And the burst happens whenever, one of these lines interact or intercept the pressure line. That's when you become a discoverable leak. It's a very simplified model, so I'm not trying to say this is how it all happens. We're trying to understand the process. This is what we found for PVC. In a typical DMA, what you're going to see is that the failure rate or the number of failures there is increasing with time. But if we now implement pressure management in year 0, as I labeled it here, what we then find in our model is that the pressure burst rate will drop dramatically. It'll stay down for 3 years, and then it will start increasing and be much closer to this dotted line shows where the burst rate would have been if we kept the pressure at 70 meters. And the solid line shows what happens when we reduce the pressure to 55 meters. So you get an initial significant reduction in burst rate, but then there's a sort of correction where that effect is reduced. This looks really interesting. Oh, just to say why this happens from our model is what you see there is this weak point there or this small leak that developed was discovered at 70 meters and repaired. If it wasn't discovered, it would have continued to weaken, and it would have been discovered, at 2 years later at 55 meters. But because we found it at 70 meters and repaired it, we're not going to find that leak at 55 meters. So there's this shadow period where the pressure reduction only leaves, doesn't have any really weak points, and there's a time before pipes start to fail again. So we were looking, and we're still looking for evidence of this behavior because the model is just giving us a conceptual idea, but we'd like to verify it with real data. And so I got hold of data from the province of Drenthe in the Netherlands. And this is really interesting. It's a single supply zone for the whole of the province because it's so very flat. 226,000 connections, 5,700 kilometers of pipes. And they did this experiment because they wanted to know what's going to happen when they reduce the pressure. So they reduced the pressure from 37.5 meters to 35 meters. So not a big reduction, but on a very big area. And this data shows the failure rate of the AC pipes in their system. And so what you see is that where the pressure management was implemented, before that you see a rise in the failure rate. Then after pressure management, you see a sudden drop. It continues to rise, and then here it jumps up and is higher, not as high as this line would indicate, but significantly higher than in this period. And so we fitted our model to this, and we could see the model can reproduce that behavior quite nicely. Now, this still isn't enough evidence that this behavior is really happening, and so we are looking for more evidence of pressure management failure rate, and we're just using average failure rate over a year, so we're not looking at seasonal effects. But if anybody has data available that we could analyze and see if we find the same behavior in that data, it'll be wonderful. So the last thing that I want to show is when the people at the Drenthe then said, well, we did this experiment. We don't really need these PRVs and to maintain them anymore. What's going to happen if we just remove them and put the pressure back up to 37.5 meters? And so we put this to the model, and this is what it shows. So this period here up to 2019 is the historical data. And then we modeled what will happen if they increase the pressure back to 37.5 in 2025. And so you see the average failure rate is around 200, under 200 in this period. But when you put the pressure back up, it goes to 1,600 in that year. And I suggested to Drenthe could they please do that, because I'd very much like the data to calibrate the model with, and they have been somewhat reluctant to do that. So that's everything I've got. Thank you, Joseph.
No worries, that was great. Thanks for that, Kobus. So just to be clear then, you are reaching out to utilities now to try and get data sort of validate and calibrate your model. That's one of the
Absolutely. If anybody's got data, and maybe they've got data on different pipe materials, maybe a couple of years before pressure management, and then for at least 5 years post pressure management implementation, and we would be very happy to analyze the data, try our models, and then report back to you. If we can use that data to further our research and try and better understand these processes. Yes. So if anybody's got data, please reach out to me, and I'll be very happy to see if we can analyze the data for you.
Yeah, sounds good. I think we can send an email out to this attendee list at the end, just with your email and your details. So there was a question in the chat from Rashad. The question, does the pipes... Okay, I think what he's asking there, is this applicable to different pipe materials? So he talked about AC and PVC there, but is it... Yeah, go ahead.
Yeah, short answer is yes, absolutely. We dug into, we found this behavior, pressure and burst rate for different materials in Auckland, and we fitted our model to the different materials based on what the calibration or what the data showed us. And so we got different materials behave slightly differently. Some of them had longer periods where the burst rate stayed down, and others shorter. But yeah, we did observe it with all the all four materials: AC, polyethylene, PVC, and cast iron.
Okay, great. I see Alan's gone off mute. Alan Lambert, don't know if you've got a question, but keep it quick. That'd be good, just because we need to leave some time for Edward.
Yeah, just a couple of quick comments, actually, if I may. The cubic relationship was mainly based upon burst reduction in very large areas. It started with Australia. And one of the advantages, as we saw from Kobus's stuff, is that if you can do a large area, then you might have 20, 30 bursts a year. Now, there will be natural variation from year to year. It won't be 30 every year. And therefore, what you can sometimes get is a particular year, maybe where there's a drought or somewhere where there's freezing conditions and there are higher bursts. And so you can be much more diagnostic if you do these tests on larger areas like Drenthe, for example. Because otherwise you're saying it's 5 bursts one year and 4 the next. Well, there isn't anything between them, if you see what I mean. And you can also do mains and services separately if you have the service data. We also see these seasonal effects are very important. And all the analysis I've done to come out with the cubic, I take 3-month rolling averages of the burst frequencies in large areas. And what that means is you can pick up the seasonal variations, and you can see when temperature and climate and drying out of the ground or heavy traffic or other things like that, where they can push the seasonal frequencies up. And where you get the extra bursts is when you get the seasonal effects on top of the pressure that you're dealing with. So the pipes seem to be able to deal with it as long as they haven't got these extra stresses of ground movement. But the really big reductions in bursts over the year seem to come from times when there's extra stress on the pipes, either because of freeze thaw or because of ground drying out and cracking and other things like that. And I can assure you, it is possible using 3-month averages and bigger systems to be a lot more diagnostic of it. But I do congratulate Kobus and his co-authors on what they've done. It's all helping us to find out more and to understand it better.
Yeah, thanks, Alan.
Thank you, Alan. Yeah, appreciate it.
Great stuff. Okay, we'll move on to Edward because actually a bit short time now. So do you mind putting up your screen, Edward? Is that all right? If you can get that working.
Yeah, sure. Can you see that okay?
Yes, excellent. Yeah, so just to introduce Edward, Dr. Edward John from University of Sheffield has a PhD, which was developed on understanding fundamental processes that cause cast iron water distribution pipes to develop leaks. And has done a lot of really cool experimental work in this area. So a nice lead on from Kobus. Go ahead, Edward.
Cool. Thank you, Joe. And yeah, so hopefully this should follow on quite nicely from Kobus's talk, kind of taking a bit more of a deeper dive into cast iron pipe fatigue failure mechanisms specifically. So this work is basically kind of a summary of my PhD, which I completed last year at the University of Sheffield, sponsored by Auckland. So there we go. Okay, so basically the aim of this work was to understand the process shown in this video, what enables water to leave a kind of a crack that is formed in the wall of a cast iron pipe, creating a leak. So it was quite a experiment heavy investigation. So we were really looking to try and understand the failure mechanisms behind this process. So as a quick overview of the presentation, go over a quick bit of background about the theory of how leaks start in grey cast iron pipes. Probably be a little bit of overlap with what Kobus has talked about. A quick overview of the methods we used, so our kind of laboratory tests to cause these pipes to start leaking, and then the results, so what these tell us about which types of corrosion pits are the most damaging, which types of loads are the most damaging, and how these failures behave. So as I've already mentioned, this work focused on grey cast iron pipes. So this was informed quite heavily by the UK context, where cast iron water pipes are still the most common water pipe material in the UK. I think the most recent version of the National Mains Failure Database show that there is about 38% of pipes by length are cast iron. So they're important for us to understand and work with, despite their age. So important things to understand about these pipes is that they are particularly vulnerable to corrosion in the formation of deep localized corrosion pits, and they're also very brittle, so they tend to crack rather than yield like a steel pipe might. And so one of the causes of both of these attributes is their graphitic microstructure. So this image on the top right is 100 times magnification, and it shows the very small flakes of graphite that you find within the microstructure of these pipes. So these kind of act like pre-cracks almost, and enable this brittle behavior. But we'll come back to the importance of those a little bit later on. So looking at cast iron pipes, what's the kind of theoretical understanding of how these leaks start? So we know that through-wall leakage is a common way that leaks form in these pipes, and that these pipes ultimately fail. So the idea is that you have corrosion pitting, which effectively removes the original metal, creating weak points in the pipe and creating stress concentrations. And then under service loading, cracks can form at the base of these pits that enable water loss and leakage. So these cracks are caused by the stress experienced by the pipe, and the stresses are caused by the loads applied to the pipe. So Kobus has given us a nice overview of these. Two that I wanted to just mention specifically were internal water pressure loading, which effectively all pipes experience, and this tends to create a stress acting circumferentially kind of around the pipe, so in the hoop direction. And also another particularly interesting one is large vehicle loads. So for smaller pipes, these can cause bending loads, and this mainly causes stresses acting in the axial direction, so along the pipe. So both of these loads can cycle multiple times per day. So this creates the possibility of fatigue cracks forming. So this is a crack that kind of forms gradually over time rather than just in a single sudden overload. And when we consider the complex loading these pipes can experience, we have the problem of stresses acting in different directions. So we could have quite complicated stress fields. So the trouble we have is that we don't really understand fully how cast iron pipes respond to localized corrosion pits in terms of how damaging a particular pit is. And we don't understand how it responds to these complicated multi-directional stress fields. So to come back to kind of the practical side of things, when we're performing pipe condition assessment, what we might want to know is which pipes are kind of at the most risk of failing. And so we could potentially figure this out through looking at the combinations of corrosion pits and loads that the pipe experience, to try and figure out which are the kind of the worst case scenarios. And so what we need to figure out is how we can assess this basically, and what information we actually need about a pipe to judge which is the most at risk, to try and replace it before it fails and stop leakage occurring in the first place. So the aim of this work was to investigate the effect of the fatigue loading type and the pit shape on the remaining life and the failure mode of corroded cast iron pipes. So the method we used was to take some uncorroded cast iron pipes, artificially add pits so that we could do that in a controlled manner, then apply either water pressure or bending fatigue loads. So this is loads that cycle over time rather than being constant, and then basically look at how long the pipe survived, so how many load cycles it took to cause the leak to start, and what the nature of the failure was, to kind of shed light on this process. So I won't go into this in too much detail now, but basically an initial piece of work we had to do was figure out how we could get a lot of pipes to test that were all very similar, because in practice these pipes vary hugely, and if you dig them out of the ground they come out in horrible states of corrosion, which we didn't want to deal with because we had our work cut out trying to understand the fatigue process anyway. So basically what we did was we were able to get some cast iron drain pipes that were produced in a very similar way to how pipes used to be produced. We did a series of tests and were able to show that they had very similar tensile and fatigue properties to the water pipes we dig out of the ground. So we use these as a kind of proxy for real water pipes in our investigations. So the pipes we tested were all about 2-inch in diameter, so a little bit smaller than pipes we see in the field. This scaling down doesn't really affect anything, because what matters is the stress that the pipes experience. So the the stress that these pipes see, if a larger pipe experienced the same stress, then the response would be the same. So we added a series of different sizes and shapes of artificial pits to the pipe. So there's been some previous research that's shown that the residual strength of the corrosion product is effectively negligible compared to the steel, the iron, sorry. So we could replicate these pits by just removing iron through a machining process. So we looked at a uniform wall loss. So this was basically just a turned down piece of pipe. We added a sharp sort of circular pit, so that had a 0.1 millimeter root radius, so very, very pointy. And also a blunt pit with a 4 millimeter root radius, so that was more of a bowl shape. And then finally on the right here, an axial pit. So this was the same sharpness as the sharp pit, but kind of extended along the pipe, because we see some corrosion pits with this form. So all of these pits penetrated about halfway through the pipe wall. So all we're varying here is just the shape of the pit, not the depth. And so the idea was to test these pits using different stress directions, basically. So we achieved this through using bending loads to create axial stresses and internal pressure loads to create hoop stresses, enabling us to look at this biaxial stress condition. So to apply the bending load, we built this piece of 4-point bending equipment. So you can see a pipe specimen in the middle there. And so we can bend the pipe and create a kind of high stress region at the bottom in the middle there where we expect a crack to form. And this pipe could also be pressurized cyclically by basically the system sort of shown in this schematic here, where we have a high pressure reservoir and a low pressure reservoir. And by opening and closing the valves, you can cycle the pressure in the pipe. And so this plot basically shows the kind of load profiles that we use. So the amplitude was constant, so the bending or pressure load just cycled basically until the pipe failed. So moving on now to look at some results from these tests. So one of the things we did was use high-speed video recordings to kind of capture the failure process to see what happened, basically. So this test shows one of the axial pits, and the only loading is internal water pressure. So if you notice the pressure scale on the top, the pressure is quite a lot higher than we see in reality. This is just because the pit only goes halfway through the pipe wall. In reality, pits probably have to be 90% or deeper to cause high enough stresses. The reason we didn't do that is because manufacturing those pits consistently would have been very difficult. But what matters really is just the stress that the pipe experiences, which you could get through a deeper pit and a lower pressure. So anyway, at the start of the video, there's no leak. The pressure is just cycling twice a second in these tests. And then suddenly we have a crack form at the base of the pit. And so this crack is basically taken up the whole length of this pit. And interestingly, it's only leaking during the higher pressure part of the cycle, and the pressure is always positive during these tests. And then after 10 cycles, the crack was able to propagate beyond the pit, and we basically have a burst. So this next video basically shows the same arrangement, but the pressure is about 75% lower, or at least the amplitude of the pressure is 75% lower than the previous test. And instead of that kind of very vigorous water jet, it's basically the same process, but just that the initial crack is much smaller. We're basically just getting a kind of dribble of water coming out. And then just to look at a very different type of failure. So this is a pipe with a uniform wall loss, and the loading is alternate bending and then pressure. So it's out of phase loading. And it's not terribly clear, but where my pointer is basically a crack has just started to form, and you can kind of see the wisps of water jet coming out of that crack. So much smaller than the crack in the initial video. And then the jet kind of gets bigger and bigger, and we suddenly have a circumferential crack forming. So that was about 9 load cycles between the crack appearing and the pipe effectively bursting. So what can this tell us about fatigue crack leakage behavior? So I think the first thing that's of interest is that the leak can start when the fatigue crack itself is only a few millimeters long. So basically very, very small cracks can cause leakage, although clearly this is very small and probably undetectable. But it's important to understand that as soon as we have a crack that spans the pipe wall, we begin to see some kind of water loss. However, Water loss only occurs when you have some kind of load to hold that crack open, when these cracks are very small. So these cracks have zero width before any kind of corrosion can occur over a longer period of time to basically widen the width of the crack. So what that means is, unless the load that caused the crack to form is present, the crack will close and water can't escape. So by going through these videos frame by frame and comparing them to the pressure, basically we found that it was about halfway through the increase in pressure in a cycle that the leakage started. So even when you've got a positive pressure, there's no leakage occurring. So this is quite interesting, and I guess provides something of an explanation for how you might have calculate a negative initial leak area for a DMA. You could have lots of very small cracks that close as you when you reduce the pressure. So looking now more at the strength side of things, so the sort of the durability of these pipes. So this shows an SN plot. So this is basically recording the number of cycles to failure for each of the tests we did. So along the bottom, cycles to failure, and that's cycles to the start of water loss. And then up the side, we have a kind of normalized stress amplitude. So that's basically the stress experienced by the pipe as a proportion of its static strength. So the first line to look at here on this rather busy graph is this solid black line here. So this is our kind of reference curve. This is if you just stretch and compress a piece of cast iron, so tensile loading. That's basically the curve that you get. So what we looked at was what happens if we use bending loading instead of this kind of standard uniaxial loading. And so this is this grey line up here and these grey squares. And actually the interesting thing here is that the bending fatigue strength is 43% higher than the uniaxial strength. So actually bending loading represents a less damaging case. So if you have a pipe that's mainly experiencing bending loading, it's probably less bad than uniaxial loading, or indeed pressure loading, because those two are quite similar. So then we added the localized pits that I showed a few slides earlier to one of the pipes or some of the pipes, and then did some more bending tests. So this was looking at the kind of the dish-shaped one and then the sort of small circular pointy one. So what we found is that these pits did cause a kind of noticeable reduction in the fatigue strength of the pipes. So localized pits do cause damage. But the interesting thing here is that there wasn't really much of a difference between the two types or the two shapes of pits. So the upward pointing triangles are the sharp pits, and the downward pointing ones are the blunt ones. So very similar behavior for the two. So it's showing us that although the pipes are sensitive to the presence of pits, the actual sharpness of the pits doesn't have a huge impact. So in this case, just knowing the depth of the pit would be enough to kind of assess how damaging it is. The next set of tests were looking at the shape of the effect of pit alignment. So those previous pits were symmetrical. Then we looked at these kind of axially aligned pits. So again, we've got our kind of reference curve here, which is just the uniaxial fatigue curve, so the tension compression with no pits at all. And then this top data set here is the axial pit with under bending loading. So that's creating a stress that acts parallel to the pit axis. And then the circles down here are the same specimen design, but subject to internal pressure fatigue loading. So that creates a stress that's rotated through 90 degrees and is perpendicular to the pit. And so even when we account for the fact that bending loading is less damaging than pressure loading, rotating the stress through 90 degrees so that it's perpendicular to the pit reduced the fatigue strength of the pipes by 60%. So basically this is showing us that the alignment of these pits can have a significant effect on the fatigue strength. So in this case, just knowing the depth of the pit would not be enough to kind of give a good estimate of how damaged the pit is. We'd actually need to understand the shape and alignment of the pit, and also what type of stress the pipe's experiencing, to understand how damaging that pit is. So the next thing we set out to do is basically trying to figure out, can we predict this behavior? So we've seen that in some cases the depth of the pit is not enough to tell us how damaging how damaging it is. So are there models that exist that we can use to predict this behavior? So we tried out quite a few different models, but I'm just showing the results of two here. So these basically show prediction plots. So along the bottom, we've got the measured cycles to failure from the experiments, and then on the left axis, we've got the model predictions. So the left-hand plot shows the net stress. So that's basically the kind of standard prediction you might do where you're just kind of assuming uniform wall loss to the depth of the pit. So even where you've got a localized pit, you just look at how much wall is remaining and assume that that's the same all around the pipe. And then on the right, we've got a model here that's using a combination of two models. Actually, it uses the Smith-Watson-Topper criterion to account for the effect of the complicated stress, the multi-axial stresses, and then also the effective volume criterion to account for the effect of localized pits. Basically, this provided pretty good predictions. So we're kind of onto something here of being able to predict this behavior and figure out which pits and predict which kind of pits are the most damaging. So just as a kind of interesting side, the effective volume approach is basically looking at how much of the pipe volume experiences the highest stresses and uses a ratio of that to figure out what loading conditions are most damaging. So although this is kind of an empirical approach, it's probably linked to the fact that we have all of these inclusions in the cast iron pipe material that act as the initiation points of failures. So if we expose more pipe material to high stresses, we're more likely to find a worse graphite flake, basically, that can cause the kind of the failure to initiate. But basically, in summary, using these models together allow you to basically predict how damaging a particular combination of pit shape and loading will be in a cast iron pipe. So moving now from that was all looking at basically predicting when a leak will begin. Looking a bit now at what we found from sort of once a leak is formed and the kind of, how it behaves, how it grows. So these show some fracture surfaces from uniaxial tests. So these were tension compression tests. And what we noticed when we looked at the fracture surfaces is that they all showed a fairly clear, stable crack growth region. So this was a bit like the PVC pipe that Kobus showed us earlier, where you have kind of this area of the crack kind of gradually growing until it gets too big and then is able to, in one load cycle, propagate all the way around the pipe. So according to classic fracture mechanics, we should be able to predict this stable crack growth region using the equation down here, which is saying that the length of that maximum crack size is a function of the fracture toughness and the maximum stress that the pipe experiences. So the crack grows by the variation in stress, but the idea is that the maximum size of it is limited by the maximum stress. So from measuring all of these stable crack growth regions and plotting them against the predictions of this equation, we found generally a pretty good agreement. There were a relatively large number of tests where we couldn't identify a stable crack growth region. So this could just be that it wasn't clear when we looked at it under a microscope, but also these tests all tended to be those which kind of failed a bit prematurely. So there might be something else going on there. But basically what this shows us is that less aggressive loading conditions with lower maximum stresses allow for larger cracks to exist, which means that effectively you can have larger leaks forming before a pipe bursts. And then finally, just the last aspect of this is just that kind of expanding on this, as comparing these two tests that we showed the videos for earlier, it's just highlighting again that when you reduce the stress amplitude by about a quarter, this test on the left leaked for about 10 cycles before bursting. The one on the right leaked for over 2,000 cycles, and we had to stop the test because of the amount of water we'd lost from the system. So reducing your loading basically allows these leaks to persist for much longer. So just to summarize, what we've shown here is that the shape and alignment of pits and the type of loading can have a significant effect on the fatigue strength of cast iron pipes, and up to 60% in the examples we've tested. So we need to consider these factors when we're trying to assess the condition of cast iron pipes. And we've developed and sort of tested out a model that we can use to predict this. And also we've shown that leak before burst behavior is possible under fatigue loading, and it's more likely to exist for longer under less aggressive loading. So yeah, that's all from me. Thank you.
Thanks, Edward. That was great. I can tell you probably had a really good time in the lab at Sheffield University basement playing with these. I've been there myself, so I know what it's like. I know it was really interesting. I think, the stuff you were talking about there about the kind of interlink between different, loading parameters kind of from traffic, bending, pressure type stresses on the pipe, and how that influences crack growth and initiation is, it's really exciting stuff. I'm just trying to think to myself, how do we deploy this in, how would a utility use this information to kind of optimize their networks of it's very, fundamental to develop our understanding of leak initiation, but what do we actually do about that as a utility to lower INRW?
Yeah, no, it's a good question. I think in some ways this work probably raises a few more questions, and I think what it kind of tells us is that to understand these processes properly, there's certain things that we need to understand and measure that we can't or don't at the moment. So I think it kind of raises there's various work ongoing to try and give much better, more detailed understanding of corrosion that exists in pipes. So instead of just giving an average depth, we need to at least know the maximum depth and preferably something about the shape. So I think this kind of provides a bit of impetus for basically improving that kind of scanning technology, but also understanding the loading. So stresses from pressure is relatively easy to understand. We measure the pressure in the pipe and we can predict those, but there's a whole host of external loads that pipes can experience, and I think our ability to predict those is quite poor generally. So I think really this is kind of a call to try and understand these the factors surrounding a pipe to be able to better manage them, basically. In the shorter term, though, I think some of the stuff around how the leaks behave kind of show some interesting things that we can kind of consider. So, you should look for your leaks when your pressures are highest, because they're less likely they'll be shut, for example.
Yeah, good answer. Thank you. Alan, have you got a quick question? Gone off mute. Oh, it's on mute. Okay, no worries. Okay, great stuff. Well, it's good timing. We're just a minute to the hour anyway. So thanks, Edward. Thanks, Kobus. That was really great. Thanks for your time putting all that together. This webinar will be on the YouTube channel, so we'll make sure that gets shared and everyone can access. I believe the next Water Loss Specialist Group webinar is next week, but we'll share more details about that closer to time. So thanks, everyone. I'll close this now.
Cool. Thank you.